Okay, so welcome to the course today. We are continuing with the topic on histogram and point operators, and last week we mainly looked into the question, what is a histogram of an image, of an intensity image, and what kind of information does the histogram provide us, for example, about contrast or about the brightness of the image. So we started, just a very brief wrap up, with saying an image is a collection of intensity values, and what we want to do, we want to make a statistics about those intensity values. Basically saying how often does a certain intensity value occur. So in this example, we would have 1, 2, 3, 4, 5 times the intensity value of 0, twice the intensity value of 128, and twice the intensity value of 255. So we can treat this as a histogram, so this information is a histogram of a gray value, is basically the number of gray values in this pixel. We then define a probability by saying what's the probability that a gray value occurs in an image. If I randomly draw a pixel, what's the probability that this pixel has a certain intensity value? Then we looked up how do those histograms typically look like. Here are a few examples for images with substantial amount of contrast, images which are very bright or dark, having less contrast, and looked into different examples of that. Then we also asked ourselves, how can we actually compute those histograms? How can we do that in an efficient way? We discussed all that last week. One important thing beside the histogram is also the cumulative histogram, which is kind of the sum of all intensity values up to a given point. So if I'm interested in this point over here, let's say 128, this means what is the number of intensity values which are smaller or equal than 128? That's what this curve tells me, which is basically the sum of all these individual values that we have in here. Then we used this, looked into what is the mean and the variance, asked ourselves how we can compute the mean and the variance, very straightforward way, and we looked also how can we actually do that in a more efficient way given we have the histogram. So this was on the insight that if we know the histogram, so if we have computed the histogram beforehand, we can actually do the computations in constant time. That means independently how large the image finally is, we can actually come up with an efficient way for computing the mean, and the same holds also for the variance. Okay, can skip through that. Then we looked into the thing, what is a point operator? So a point operator is a function which maps one image to a second image by changing its intensity values in a way that this mapping only depends on this single input pixel and not other information from this image. So if I want to make the mapping from the image A to the image B, for this pixel ij, I only need to look into the pixel ij of the other image. I don't need to look into the neighborhood, which would be a local operator, or into the overall image, which would be a global operator. And we defined this as these types of functions, and we will actually look into those functions today in more detail. So we had our output intensity value for an image coordinate ij, which is the input image transformed through a function or through our operator, and these operator can have some additional parameters. And we looked into a very basic setting, which is basically using a linear function. So then our function f has the parameters p, which is the number k and the number m. And this is simply a linear function mapping this intensity value a to k plus m times a. And we looked if we have this value k, if we increase the value for k here or take a positive number, the larger that number is, the brighter my image gets because it increases the brightness. And if I take a negative value for k, it reduces the brightness. And we also have seen that depending which value m takes, we can actually increase or decrease the contrast of our image. We have all done that, have seen a few examples. So if the intensity, the identity function is our mapping, nothing changes, the histogram stays the same. And if we use different functions for our operators, basically this image is transformed into those images. We looked about foreground-background separation until we ended up with quantization and what we discussed. So what we discussed last week, just as a very brief wrap-up. What is an histogram of an image? What's the mean, the variance, and the median? What do they tell us? Basically, it's brightness and contrast. And we looked into the question, what type of functions can we apply to transform one image into a second image. And for now, we are going to continue with this topic, and are especially interested in the question, if we have a function f, how does this function f changes our image, and especially how does this change our histogram? So consider we have a function again, f, which maps from A to B, from our input image A, generates an output image B, and we assume that's a monotonous function. That means the brighter the, so we don't flip intensity values. So either all intensity values, so if I have an intensity value A1, which is smaller than A2, also B1 will be smaller than B2. So that's not that we make so change the order of the intensity values so that we have an intensity value which was whatever 1 before, it is 10 afterwards, and the second one which is mapped from 2 to 3, for example. So this is the only assumption that we make. So we have our histogram of the input image, which is called HA, so the index A for the input and B for the output. And what we now want to do is we want to compute the output histogram without looking into the image, just looking to the function f. And we want to understand how does one of those point operators actually change the histogram. If we understand that, then we can actually turn that around later on and say, given that we want to have a certain desired property of our output image, how should this function f actually look like? So if you, for example, want to have a certain brightness or want to have a certain contrast, just by looking to the histogram, we can actually define this function f so that the output image then has the desired properties. And I want to start with an example over here on what we are trying to do. So consider what is shown down here, kind of just flipped upside down, is our input histogram. So this is our input histogram. This is the intensity values A, and this basically means how often do these intensity values occur. I just kind of flipped it upside down to make it, to put everything into one single image. And what we have here is kind of the output histogram, so histogram B. So is there any question there in the back where I can help you understand that? Okay. So this is our output histogram that we want to have. And what we see here is our function f of A. And if you now put all those plots into the same image, we can actually get a quite nice understanding how this mapping works. So if you have an intensity value here, let's say this could be 200, and this is simply how often does this intensity value 200 occur. We look it up, where is this function, this value A mapped to through f. So what we have here, the y value is now f of A. And so this will be the new location, which is also called B, because B equals f of A. So we have, this is then the number of times the intensity value occurs. And the important thing is that kind of the gray area in here and this gray area in here must be the same, because I'm kind of not changing the pixels, the number of pixels that I have in here. So this is kind of, you can see this as the kind of the area, the gray area here, which consists of the width or the spectrum of intensity values I'm looking into and how often do they occur. I map through this function f into this box. So here, this area and this area must stay the same. So this is kind of the important thing for our mapping. And so I can simply use this illustration to understand how the first histogram is transformed into the second histogram with the point operator. What I do is for every point in here, or for every kind of small bucket or bin, because in the end we have, in our example, 256 different bins here, I say, okay, this bin is transformed under this function to this intensity value. This one is mapped to this one. This one is mapped to this one. This one is mapped to this one. And this is kind of how we can very nicely visualize those operators. And if we consider that this function f of A is now a straight line, and let's say it starts in 0, 0, and we have a slope of 1. So if k equals 0 and m equals 1 in our example before, then it's an identity mapping. So then this function down here is exactly the same shape as this function down here. So what happens if I reduce the slope? So I say m not equals 1, m equals 0.5. What is the effect on the output histogram? So that means my function f doesn't look in this direction, but now it looks in this direction. Here, my line, my straight line. So this would be approximately m equals 1, I take m equals 0.5. So this is my function. What happens with this histogram down there? Yeah? Exactly. I'm kind of compressing the histogram in terms of its input values. So if this is then 255, from 0 to 255, this is mapped into the interval from 0 to 128. So I kind of basically compressing the histogram. Okay, if I now take a value of 2, what happens then? Yeah?
It's very bright, I would say.
Yeah, so I'm actually stretching the histogram. So I'm not necessarily increasing I'm also increasing brightness in this sense, but typically I have to crop it. That's true. But the important thing is that, because I'm changing the mean, but the important thing is if I look to the distribution of values, I'm basically stretching the histogram. Okay? And stretching the histogram means increasing the contrast, and compressing it means reducing contrast, because contrast is kind of the difference of those values. Okay? What is the question? Ja, klar.
Also wenn ich das jetzt vergrößere, also wird das von einer B-Achse länger dann jetzt, sag ich mal.
Genau. Also wenn ich jetzt
und habe dann mehr als 255 Werte?
Das können wir jetzt erstmal ignorieren. Also wenn wir jetzt einfach nur die verstehen wollen.
Keinen Sinn dann in dem Sinne, oder?
Wenn ich jetzt sozusagen nur ein Bild hätte, was 256 Werte haben würde, wäre das natürlich jetzt ein Punkt. Aber wenn ich jetzt mir erstmal, das erste, wo es um das Verständnis hier geht, ist, wie transformiert diese Funktion f meine Input-Funktion in eine Output-Funktion.
Okay, und die Information ist jetzt, da die Funktion f so aussieht, wie sie aussieht, momentan exakt dieselbe in dem linken oberen Teil wie in dem unteren Teil.
Genau, also hier, was hier passiert, ist sozusagen in diesem Bereich wird das Histogramm breiter gezogen. Also hier ist es ja relativ kurz.
Ja.
Das wird hier breiter gezogen. In dem Bereich wird es zusammengestaucht, weil die Steigung hier kleiner ist als 1. Okay. Hier ist die Steigung wieder größer als 1, da wird es wieder auseinandergezogen.
Also mit der Funktion f, ja, okay.
Genau. Und es geht sozusagen bei diesem Bild darum, um zu verstehen, wie diese Funktion f das Histogramm verändert. Ja.
Das heißt, dass das B-Histogramm jetzt so hoch, also so gedreht da liegt, das ist nur zur Veranschaulichung.
Das ist nur zur Veranschaulichung. Das ist einfach, wenn man das macht, deswegen das auch nach unten geflippt. Das dient einfach nur dazu, um das alles in einem Plot zu visualisieren. Weil ich sozusagen ja von der x auf die y-Achse mappe und dann muss das auf der y-Achse liegen. Also das sozusagen dient nur zur Illustration. Wenn man jetzt sozusagen das Histogramm hier unten hin plottet, die Funktion f daneben und das Histogramm an dritter Stelle plottet, sieht man diesen Effekt nicht. Kann man das, oder meiner Ansicht nach, deutlich schwerer illustrieren, wie das aussieht. Okay, so the key take-home message from this thing is that those areas actually must stay the same. So if those areas actually stay the same, it's kind of the number of intensity values that we have in the interval from A to A plus some dA must be identical to the number of intensity values I have in the interval from B to B plus some small dB. So if I just look into the area, I can say, assuming that this is kind of a linear, so straight function, if these blocks are kind of small enough, let's say this is kind of one bin of my histogram, then I can say the function value that I have in here times the width, this dB, should be the same as down here. So this basically means the area stays the same. Okay? So this value corresponds to this value over here. This value corresponds to this value here. This value is this value, and this value corresponds to this value over here. Okay, so what we now simply can do is we can divide or compute the ratio that we simply take this equation, divide by dB. dB moves down here. Then we can actually write this at this ratio. And this absolute value I need to take into account because I don't want to get negative intensity values. Because we're just looking to the area over here. Okay, what does dB divided by dA mean? for this function f. Yeah?
Something like expression of compression ratio.
Yes. So what is dB divided by dA means for this function at this location? Yeah. Yeah. So the first derivative, it's a slope. So or the slope, and as we have a general function over here, it's the first derivative. So this part down here is simply the first derivative of this function. So we can actually write this as the input histogram and the first derivative of my function f. So what we now have is we have a relationship which tells us how's the original histogram transformed into the new histogram through the function f by basically looking to the first derivative. Okay. If you now just look to the function itself, we say, okay, we have a function which depends on b, and then we have some values, but they don't depend on b. It's a bit stupid, right? So we don't know which values of a to fill in here in order to compute this value for hb. Any idea what kind of values for a we need to put in there? So of course we need to have this correspondences between a and b, and this correspondences a and b is given through our function f, because what we are doing, we are mapping from a to b. So what we have is basically b equals f of a. So we have the relationship b equals f of a. I have my function which only depends on a. So what I basically need is a equals something. How do I get that? Nope. Yeah?
I need the inverse function.
Exactly, I need the inverse of f. Because if I write f minus 1 of b equals f minus 1 of f of a equals a. Oops. Okay, so I say, okay, now I simply need to replace this a over here by f inverse of b. So that's the case. F inverse of b equals a. So I can now change my function, though this function nicely depends on b. So now if I put a b in here, I have my b's in here and don't depend on any other variable. Okay? So now to compute the transformation, what I need the inverse of f, and I need to compute the first derivative of f. And if I have both of those values, I can actually directly compute how the original histogram is transformed into the new histogram. Okay? Okay, let's make an example and consider that our function f is basically the linear function that we are looking to before. So we say, okay, b equals f of a is our k plus m times a. So we can compute the first derivative of this function. The first derivative, so if I compute the first derivative with respect to a of this function, k goes away, and in the second part just m remains. So I obtain the first derivative of f is simply m. The other thing I need to do, I need to compute the inverse of f. And the inverse of the linear function is specified here. You can just verify that by computing f to the power of minus 1 of f of a. So what I have is b minus k divided by m. So this is my inverse function. And then b needs to replace by f of a. So this is f of a minus k divided by m. So an f of a is k plus m times a. So this is k plus m times a minus k divided by m. So this goes away and this goes away, and then m goes away, and I keep a. That's what exactly this should be. Okay? So given this equation, you should trust me that this is the inverse of this function over there. So if I do that, this leads me finally to this expression over here. So for every value of this histogram, that means the number of intensity values in A, in the input image, I do this computation and get the corresponding output value. So for generating my new histogram, what I need to do is I need to go from B from 0 to 255 and compute the corresponding value just by this expression. So putting in B from 0 to 255, query the corresponding value from my input histogram, and then get my output histogram. So what this exactly does is a shift by k in intensity values and a scaling by m, because this was our linear function. Okay? So now we have kind of an understanding how a function f transforms one histogram of another histogram. So if I want to transform one image into another image using my function f, and I cannot directly say how the histogram changes. Now I can actually turn that around and say, okay, maybe I want to have a certain requirement about the histogram of the output, because I want to achieve a certain distribution of intensity values. What shape should f have in order to achieve that? This is kind of the next function what we can do. So we want to change an image. So this is an image, just a photograph. And these are the intensity values we have over here, and the cumulative values. And what I want to do now, or the problem with it, what's the problem with this image? Let's start in this way. Why is this maybe not a good image?
It's not bright enough.
It's not bright enough, maybe. Maybe not. What's kind of more disturbing than brightness in here? Yeah, it's a lack of contrast. It means all the intensity values concentrate on a very small range, in this example, whatever, from 120 to 200. So all those intensity values are concentrated in a very, very small region. So what I can do now is, what happens if I would take this histogram and stretch it? The result would be that I would get an image with a higher contrast. But maybe I'm not only interested in kind of simply stretching this histogram that it takes all values from 0 to 255. Maybe I want to get an equal distribution of intensity values over the whole spectrum of intensity values. It kind of, let's say I consider small buckets, let's say of 50 intensity values from 0 to 50, 50 to 100, 100 to 150, and so on. I want to have approximately the same number of intensity values in those buckets. So they get a uniform distribution of intensity values over the image. So that means basically that the intensity values in the output image are equally used. So I have the same number of intensity values with the value of 1, of 2, of 3, 4, 5, and so on. Of course, I have a discretization here, so it's not exact, but approximatively. If I actually do that, I obtain an output image which more or less looks like this, which you should at least see that it's typically visually more appealing, at least visually more appealing. And we can also identify certain properties much better if we kind of transform our image in this way. This is something which is called histogram equalization, or in German Histogramvererbung, which is one standard technique for changing intensity values of those images. And what I want to do now in the remaining part of this lecture here is actually to look into the fact, how do we compute this transformation to go from here to here by basically specifying what the output histogram should look like. So what I do here now is I have an input image and I want to specify a certain output image, which is basically uniform distribution over those intensity values. And how does this function f look like so that I actually achieve that? I need to know this function f in order to actually do this transformation. Okay? So if I say my output histogram should have the same number of intensity values for every bin. What I can actually say is that so I before had the equation this h of b should equal HA of A dB divided by dA. This was the equation that we had before. So if I say every bin of the output histogram should actually have the same value, so this should actually be a constant. Right? Because one has the same number of intensity values in every bin. And then I can actually now, saying that this should be a constant, I can actually specify how this function f should look like. So let's have a look at how that works. So what we have written in here is basically exactly the same what we have written in here. We're saying simply this is 1 divided by k. Just my constant. This is kind of the number, the values that I want to have in every output histogram. Every bin of the output histogram. And if I say, okay, this function f is now monotonically increasing, I can actually ignore this absolute value. Because if it's monotonically increasing, this is always positive. So I can simply skip that over here. So then I can actually move this dA up here, multiply by dB, and multiply with k. And if I do that, I actually obtain this expression over here. And then I can basically integrate both sides and solve this equation by integration. So simply integrate over here. So I get my value of b. I have my integral over this values a. So there's the alpha in here and integrate from 0 to alpha equals a. I have my factor of k that doesn't change, and I have my integration constant, c over here. Okay, so this is just by integrating, I go from here to here. And now I can say, okay, let's have a look to this integral over here. So it's just a copy and paste from the image. So this is the integral part over here. And this block over here is nothing else than the cumulative histogram of my input image. So I'm basically saying how many intensity values from 0 to a certain value A does occur in my image. So if I'm living in a discrete world, I can replace this integral by my sum. So it's the sum over all intensity values from 0 to A, which is exactly my cumulative histogram. So this equation turns into just a factor k of the cumulative histogram plus a constant c. What I've now done is I've said, okay, given that I want to achieve that the output for every histogram bin is identical, it's 1 divided by k. That was a constraint that I put in. Can make some transformations, say, okay, then this is what my mapping must look like. So based on the requirements that I have, I can derive what my transformation should actually look like. Is this clear up to this point, what I've done? So I said, I want to have a certain constraint on my output. I have my given input, but I don't know how the transformation looks like to transform the input into my desired output. I can specify a constraint that I have for my output. So exactly what I've done there. And then I can try to solve this equation. In this example, I can actually solve that quite easily. And this transformation basically takes into account the cumulative histogram of the input image and uses that to specify what the output function looks like. Am I ready yet? So could you apply that directly? Why not?
I have to less parameters.
So I don't know k and I don't know c. That's true. So how should I determine k and c? Any idea? How should I set it? What other constraints do I typically have in my image? This actually relates to the question that you had before. So what kind of constraint do I have in my standard JPEG, PNG, or whatever image? Yeah?
So k should be the number of pixels divided by the number of bits.
That's, of course, it's in the end kind of one constraint. I don't have more intensity values than pixels, but that doesn't, I don't think that this will help me here. What's another constraint that I have? I can't deal with intensity values which are smaller than 0, and I can't deal with intensity values that are larger than 255. That's a constraint which I haven't used in here. If I want to have an equal distribution over a certain range of numbers, so far it just said I want to have a uniform distribution, but it didn't specify over which kind of input values, intensity values. What I now can do is say the smallest intensity value should be 0 and the largest intensity value should be 255. And I basically can use those two constraints to set my parameters k and c. So I start with this equation over here, need to determine k and c. And what I want to have is that the b of 0 should turn into 0, and b on 255 should turn into 255. So I can express this now, saying this is b, this is kind of the output that I have for 0. So this equation should be 0, and in the end it should up at 255, where h of 255 is n, is the number of pixels that I actually have. And if I do that, I can simply solve this equation. I get my parameters k and my parameters c. It's basically a simple way to compute those values. And now let's have a look how this looks like. So I had this house, which was my original input image. This is now my function which transforms my input to my output. And the function actually looks like this. And this function has this kind of this weird shape because it depends on the cumulative histogram of this input image, because I have the cumulative histogram in here. And this depends on the input image. So I transform all those intensity values in this way, and then I turn this image into this image over here. And what I have, for example, is that I now use the spectrum of intensity values much better than I was using it before. And you can see much better contrast, although you may not see that on the projector here, but you should actually see that in your printouts, between those two images. And what I've shown in here is actually the equalized histogram, so the output histogram that I have in here. And that's the first thing when that made me wonder, saying, why should that be the equalized output histogram? What was my constraint on the equalized output histogram? What's the constraint I started with? Yeah?
You have the same amount of spikes per bucket. The buckets are 5 or 6 now.
So what I want to have is want to have actually a uniform distribution over here. But that's not really a uniform distribution.
Because we have different amounts of values within each bucket.
Exactly. So the constraint that we have in here is that we actually have a discretization in here. So if I have smaller values over here, that means those values are much denser compressed. So just have to look into kind of my small bucket. So if I see this as a bucket, the larger I make the bucket, the more this actually turns into the uniform distribution. And this is a result that I have from having this quantization of intensity values. That is not a continuous function that I have in here. Also, this function is not a continuous function. I only have 256 intensity values, and this leads to these effects. Because it basically means if I, for example, have in the input histogram all zeros, but just one peak, it means I just have an image where the whole image has the same intensity value. I can't break that up. I can't break up one bucket in my input image. So consider I have a completely gray image, and my histogram would be 0, 0, 0, n, and 0, 0, 0. And whatever function I transform that, I may change the intensity value that the whole image has, but the whole image will still have exactly the same value. And this is the reason that I basically can't split up an input bucket of intensity values, because I have this quantization of intensity values. If that would be a continuous function, the equalized histogram wouldn't look like this. So what this histogram equalization basically does is it typically increases the contrast of my image because it uses the full spectrum of intensity values that is available and tries to use all buckets of intensity values in exactly the same way. Just for typically, because for typical images, if I look to extreme cases where I have a couple of values concentrated over here and a number of values concentrated over here and the mean is somewhere in the middle, I may reduce the contrast. But in typical real-world images, I actually get increase the contrast. And what it basically does, it takes those intensity values which are somewhere concentrated in the input image and equalizes them out over the whole spectrum of possible intensity values. And this is again one of those examples, or my example I started with. So this is the original input image and input histogram. And so this is kind of the cumulative histogram now, which is approximatively a straight line. And these kind of small steps over here is just an effect of the quantization. And again, so I have smaller values here, but these are simply closer together. And here there is simply a larger difference in the intensity values. And this is because I can't break up two intensity values, which I take exactly the same value here in the input image. I can't break up the bucket. They will still stay in the same bucket. And the larger the spacing is here, the higher those values actually get. Okay? So the next thing I can actually do, I can also do, is noise variance equalization. So if you remember what we told last week or 2 weeks ago, we looked into the standard deviation that I obtain if I measure intensity values. We have seen that the variance depends on the measured intensity values. What I have here with an image is basically a grid of intensity measurements. And all those different measurements have a different variance. The variance depends on the intensity values. Another transformation which is very popular, especially if one wants to do an image analysis later on using statistical tools or statistical methods, I'm interested in having, or it can simplify some of the computations that I do if I know that all my input values have the same variance. So that all my measured values have the same variance. It simplifies some of the things I can do. So what I now can also do, okay, let's simplify the mapping which maps my input image, just the real world image that I took from my camera, into a new image in the sense that all measurements of intensity values have the same variance. And so what we're next trying to do is actually define a point operator that actually performs this variance equalization, or Varianzangleichung in German. Okay. Okay, how's it written down there? The first assumption I start with is saying that the variance that I have basically only depends on my intensity values and a constant factor, this one over here. So what I basically ignore here was the noise from the electronics and the noise from the rounding operation, because I said this was actually comparably small noise that actually has been introduced. So for this computation here, I basically skipped that, but we could take that into account, or we could even take more complex relationships here into account. But under the assumption that the Poisson distribution was a good model for the number of photons that we actually measure in our individual sensor cells, we actually have this relationship that we have, that the variance of the individual intensity measurements is actually a constant times the measured intensity value. So this model is not just a random assumption, it's based on the Poisson distribution. And the goal is that the variance or the standard deviation in my output image is a constant. So it takes the same values, sigma 0, it's the same for all intensity values. So it should not depend on the measured quantities anymore. Now I can actually start in a very similar way. So I can say, okay, how's the variance propagated through error propagation? Through, in this case, if I transform it through a function, it basically depends on the first derivative of my transformation function. And so I can say, I still say I use a monotonous function. So again, can get rid of my absolute values over here, and then I simply have the very simple relationship that I say my output variance, which should be constant, should be the first derivative of my transformation function and the variance of the input intensity values. So so this depends on every measured intensity value. This is non-constant, and this should be constant over all elements. Okay, so this was just a copy-paste from the previous slide, and we have our copy-paste of the assumption between the relation of the variance and the measured intensity values. Okay, what I now can do here is I can simply multiply by dA, dA moves here, divide, dA moves here, divide by sigma A, goes down here, so I end up having this relationship over here. And I can say this element, simply the square root of this expression, goes down here, which directly leads me to this equation. The only thing I've done here is I've written this as square root of m and this a to the power of minus 0.5. So this is kind of the function that I now need to solve. And I can simply, by integration, again solve this expression over here. And it's actually a very simple form that the integration leads to this value, which is the original function just with a factor of 2 here. We can just show that this is actually the correct result if you just compute the first derivative of this function and see that we come up with our original function. So if I have this expression over here, this is equal to 2 times sigma 0 by square root of m times, and this is the square root, so this is a to the power of 0.5 plus some constant c. And what I now want to do is I want to compute the first derivative of this function, and this is simply, so I have to take 0.5 times 2 sigma 0 square root of m, reduce this by a value of 1, a to the power of minus 0.5. And so this goes away and this goes away. And this is exactly the original function that I have in here. So this means this is the first derivative of this function. Therefore, this is the integral of this function over there. Okay, and now I have a transformation from one image to another image. I want to say what I want to maintain from this mapping is actually that an intensity value of 0 is also mapped to an intensity value of 0 from the first image to the new image. So say, in order that B of 0, A of 0 is mapped to 0 again, I said C to 0, because then this additive constant goes away. So if this one is 0, also B will be 0, the corresponding intensity values. And then I choose my output variance in a way that the intensity value of 255 is also mapped to an intensity value of 255. So what I basically do is I define a transformation and I fix that 0 is mapped to 0, so the minimum value, and the maximum value, 255, is mapped to 255. Because I don't want to let intensity values go out of my spectrum. But what I do is I change the individual intensity values in a way that I have this constant variance. And so by these two constraints, I can actually set my two unknown parameters over here. And this was a parameter which is specific to my camera. This is a result from the noise model. So this actually leads to a square root function, which is actually depicted over here, how this looks like. So I start down here and I end up here. This was the constraint that I introduced. And this is a function which is basically a square root function. And so this maps this image into this kind of image. And the important thing is that now in this output image, for every measured intensity, I have exactly the same variance. Sorry, what? Also, okay, so it doesn't mean that this image now looks nice or looks visually more appealing. The important thing is this, the intensity measurements that I have here now all have the same variance, the same noise. And this simplifies the analysis of those images if I use statistical techniques where I want to reason about the different intensity values that I have. If I know that all my measurements have the same noise, that actually simplifies some of the computation that I need to do. So I can also do that in the general case. I don't need to have this kind of simplified form. So if I have a more, this basically is if I have a more complex model for my, for the variance of my intensity values, so not m times a, then the expression gets a bit more complicated. I have a general function over here, and then I need to basically, I need to integrate this more general function. I just could solve it in this easy form over here because it was just m times a. And this again, this is something which is often used if I want to analyze aerial images and want to reason about the different intensity measurements that I have and analyze those images. The Varianzangleichung or variance equalization is one of the techniques which is often used as a pre-processing step. So this was kind of one part of the point operators by saying, okay, by analyzing the histograms and adding constraints to the output that I want to have, I can actually define a function just by reasoning about those histograms so that the output image has certain properties, or especially the output histogram has certain properties, what we were most interested in so far, which was the uniform usage of intensity values, or in the second example now here, the uniform noise in the transformed image. What we so far looked into the point operators which map from one image into another image. But we are not restricted to those. We can actually also define point operators which map two images into a new image. So what I can also do is I can say my output image is actually the sum of the intensity values of two other images. It's basically like if you have your graphics programs like whatever Photoshop, and you take two images and overlay them in a transparent fashion. Then you basically add those two layers. It means you simply take the corresponding intensity value in the first image and the second image, and then you multiply them up. Or you can subtract them, or any other operation that you can actually do. And one which is quite frequently used is something which is called masking, where I say only if certain properties are fulfilled in one image, I actually copy the output of the second image, or I set it to 0. So what this function does is, if the image A1 has a 1, it basically means use the intensity value of image number 2. Just copy over my intensity value from my second image, A2. Otherwise, set it to the intensity value of 0. So what I have is I have one mask. The mask is here, the image A1. Wherever A1 takes a value of 1, I'm basically copying over the intensity value of the second image, and everything else is set to 0. The other thing I can do is I can actually combine those values. So I can take 3 images in input and say, whenever the masking image takes a value of 1, take the intensity value from this image, and otherwise take those of the second image. So I can, for example, use the foreground of image number 1 and the background of image number 2 and put a new, whatever, person in front of some new foreground. In front of some new background. By taking the background from this image and the foreground from this image. So this is, let's say, an image of a person. This image has everywhere where the person is in this image number 2 a 1, everywhere else a 0, and this is whatever, just a beautiful view of the countryside image. Then this person will be set in front of the background of my countryside images. So the only thing I want to point out that there are a large number of different ways that I can use those point operators to transform images, to combine images, to do kind of if-then-else statements of images by masking some parts out and adding some other parts to the images. In general, we can say that those point operators are, of course, only a subclass of operators. So Not everything can be expressed by through those point operators, but one of the advantages that they can be very, very efficiently implemented. Because what I basically need to do is I just need to have a mapping from all the intensity values which range from 0 to 255 and say an intensity value of 0 is mapped to 0. An intensity value of 1, for example, mapped to 2. A value of 2 is mapped to 4. So I just need to compute one single stupid lookup table, and then I just can use this lookup table to transform one image into another image. So this is something which I can do very, very efficiently. And also I can store those point transformators very efficiently because they only depend on the number of intensity values. And at least as long as I use standard images with 8 bits depth in those images, that means 256 different intensity values, that can very compactly be stored. But of course, if I have a much larger number of intensity values, this advantage substantially decreases. Nevertheless, computing this lookup table is always possible as long as I have so many intensity values that can store that in memory. I just have to compute a very simple lookup table and then compute all the transformations from one image to the other image. That's it from my side for the first part of the course for today. So what we in sum looked into, you should know what the histogram of an image is, what the histogram tells me about the image. What are simple operators which transform one image into a new image? How does this affect the histogram? Which kind of constraints can I easily formulate, or examples for constraints that I can easily formulate so that the output image has certain properties which I want to have in order to continue analyzing this image or make the image visually appealing or increase the contrast so that I can easier identify the different objects, for example, that I have in my image. And yeah, what I illustrated were at least two very prominent examples of such operators, which was one kind of distributing the intensity values over the whole spectrum of possible intensity values, and the second one transforming it so that I get the same variance in the individual, for the individual intensity measurements. That's it from my side. We make whatever 10-minute break, and then we are continuing with binary images. Thank you.